Okay, we are discussing the introduction on alternative routes of iron making for direct reduction and smelting reduction process, and I am just continuing from the last lecture. Okay. So, this is the lecture number 52 and previous one was 51. Okay. So, we have talked about the basic definition of the DR processes and its reaction involved, and now I am talking about some of the DR technologies that are available. Okay. So, direct reduction technologies. So, you can see here on the left hand side, these are all fluidized bed technology. Okay, fluidized bed based technology. First is called the fire process. There is the fluidized iron ore reduction. It is a US technology, USA technology. And then Finmate is also a similar technology. It was developed by Voestalpine of Austria as well as Venezuela one company. So, it was a Finmate. Okay. This is also fluidized based technology, fluidized bed based technology. Okay. Both fire as well as Finmate. And only difference in case of the Finmate, in case of the fire, fire is also, first let us tell me about the fire process. In the fire process you have fluidized bed reactor and then they are in series, around 4 or 5 reactors are in series, and in the first reactor basically some preheating is done by natural gas. By burning the natural gas you can preheat it, and then the 3 reactors are in series and you reduce it. Okay. And the reduction gas entered through the last reactor and then it cascades through the other reactors. Okay. So, and reducing gas is basically the reformed natural gas that is used. And in case of the Finmate process, the only one difference is that the preheating is done by the off gas from the other reduction unit. Okay. Not in case of the fire process is the natural gas heating is required, but here you recycle the off gas to preheat the material and some other process variant may be there. So, otherwise both are the fluid based reactor. And then Sarco-Red, this is also another process. There is a fluidized bed reaction process, is called the Sarco-Red process. And so, here what you are using, there is a reductant gas, is basically natural gas, you deform it and you can directly use the fines because it is, these are all the fluidized bed reactor. And so, iron ore fines and the natural gas you can use it. And another reactor, another also you can produce the iron carbide also, if you just iron ore and then you can produce the iron carbide directly from there, and then iron carbide is also a feed to the electric arc furnace. Okay. So, these are the fluid bed reactors are there, these are the thing. Okay. And these are basically based on the shaft furnace. There is the Midrex and HYL3, that is these are the process. Not only HYL3, all HYL process are in the category of the shaft furnace, HYL3 and then HYL4. HYL1 was different because that is based on the batch shaft furnace. So, otherwise Midrex, HYL3, HYL8 all are based on the continuous shaft furnace. And so, these are basically the shaft furnace process, and here you can use the natural gas, you can use the pellets, you can use the lampior also. Okay. And these are the shaft furnace based processes are there. And then you have this process SLRN, Quadir, DRC, Alice-Chalmers controlled process, Alice-Chalmers process, then TDR Tata direct reduction, Jindal direct reduction, Odisha Sponge Iron Limited direct reduction, all are some patented processes are there, and where basically it is all are rotary kiln based processes, rotary kiln furnace based processes. Here the feed is basically coal and the lumpy ore. You can use some pellets, but rarely it is used, whereas in the rotary kiln it is basically the lumpy ore and the coal that is used. Okay. And SLRN is the Lurgi, that is the Germany technology, and this is the process. Lurgi initially it was, and it is widely used rotary kiln furnace based process or DR process. Besides, in India you can see lot of process has been developed like TDR, Jindal, OSIL. These are the Indian patented process, and Alice Chalmers, this is also a Canadian patented process where basically you have, instead of the coal, you can use the natural gas and oil, and you can control the carbon percentage of the DRI to some extent. Usually the coal based DRI is very low carbon is there, 0.15 to 1 to 0.1 to 0.2% carbon may be there in the coal based DRI, but you can, by controlling or using the natural gas, you can increase the, by cracking of natural gas you can generate some shoot carbon, and anyway you can increase the carbon content to some extent in this process. All this process has some process variant to some extent, more or less, and all this process variant may be about the size of the coal you are using and the location of the tuyeres, location of the burners, and then those are the things, and the size of the coal particles that you are using, or the proportion of the coal, how much in the direct reduction coal, how much is the burning coal. Okay. So, those some process variants are there. Otherwise, all processes are based on rotary kiln, and you are using the non-coking coal, lumpy ore, and sometimes pellets, but rarely used pellets, and you convert it to the DRI. Okay. So, these are the coal based processes are there. And then whatever the processes that I am going to tell, these are the processes other than the rotary kiln furnace based processes. For example, INMETCO and the FASTMET, these two processes are based on rotary hearth furnace. As you saw, there is a rotary hearth furnace. What is there? In the rotary hearth furnace is a donut shaped reactor, just like a donut you have seen it reactor, and here the material moves over a rotating hearth in a circular periphery. Okay. So, you put the material, it is the material does not move itself, it is basically the rotating hearth that carries the material over 360 degree and then make it out through a gate very adjacent to the inlet gate. Okay. So, this is called, and during the, when the hearth is rotating to a 360 degree, it basically traverses different temperature regime like preheating zone and then reduction zone and then cooling zone and then finally come out. Okay. So, it is very similar to the blast furnace where the material, when it is coming out, it goes through different temperature regime. Here also the material goes through different temperature regime, but the main difference is that the material itself is not moving. Okay. It is the rotating hearth that is carrying the material through the different temperature regimes. That is why you can compromise with the quality of the raw material, since the material is not moving, because if the material physically move, then they undergoes impact and abrasion and generates the fines, okay, and hinders the reduction process. So, in case of the rotary hearth, that problem is not there. So, you can use any kind of low grade raw material also you can use and it can move. Okay. So, that is there, and that is why you can see in all this process you can use the waste oxide, that is the most important. All this process use the waste oxide. So, INMETCO and the FASTMET are based on basically rotary hearth furnace based process. SITCOMET is also rotary hearth furnace based process. Here basically the input in this INMETCO and FASTMET, the input is iron ore coal composite pellets. These are the composite pellets is the input, and in case of the SITCOMET, it is not the iron ore coal composite pellets, but rather it is the fines are used. Okay, both the coal fines and ore fines are put on layers, and then it is also mixed up by a rotating device. But this process could not be okay. This process is not become very popular that way because of some technological problem involved in it. But INMETCO and FASTMET are very commercialized, very much popular process till now. Okay. And sarcophore is a process. This process is based on fluidized bed. Okay. You gasify the carbon and then you use it for reduction of the fines in a fluidized bed. Okay. So, sarcophore process is basically based on, it is a coal based as well as fluidized bed based process. Okay. Sarcophore process, here basically use the coal and reduce the iron ore in a fluidized bed. Basically you gasify the coal there. So, this is the sarcophore process, and the Primus process, it is basically based on, there is a multiple hearth furnace process. multiple hearth furnace, you can see there is the form number of hearth is used, and the multiple hearth furnace based process. Here it is also a coal based process. And so all these processes, basically finally what happens, the most interesting thing to see is that you can use the waste oxide, you can use the fine ores, you can use the coal in this process, non-coking coal you are using it, and you are producing what is called the low metallized solid. Basically in this process, since you are using the waste and all this thing, here the idea is to metallize it, okay. So you can produce about 70% metallization, 70 to 80% metallization you can get out of it, okay. In this process you are using the waste oxide, and also you are not keeping for a longer time, you are producing first and then getting the low metallized solid, and then what you are doing, basically you are melting in an submerged arc furnace, because it contains a lot of gangue material, okay, lot of gangue, so it will generate a lot of what is that called, that is your slag. So gangue has to be separated in the form of slag metal separation, a lot of slag will form. That's why it is better to use a submerged arc furnace, and then you can separate the gangue. So when you separate the gangue, and also during this process also you reduce to some extent, because lot of, since it is 70% metallized, 70 to 80%, lot of iron will be connected with the oxygen in the form of wustite, FeO. So you reduce also using some coke, you can reduce those coal, some carbon, using some kind of carbon, you can reduce this FeO to refew back to the iron, okay. So that's why you can, it will have some reducing atmosphere, so that, and when you do that, some other impurity also will come into the liquid iron, and then whatever you produce, it is called the synthetic hot metal. So it is similar to the hot metal composition, and finally you can purify this hot metal into the electric arc furnace, okay. Or the coal based, gas based, there is the coal based rotary kiln furnace based process, and then product of this, product of shat furnace, product of fluidized bed, everything you can get it to the electric arc furnace and melt it. So, and also this thing, there is the, you can know there is the fluidized bed, what is the product is, all most of the cases they are briquetized, okay, they are briquetized, and then they are put into the electric arc furnace. And the one major difference between the fire, finmelt and the sarcodate process is that in case of the sarcodate process, in the fluidized bed process, the major problem is the sticking of the powders. When you are fluidizing this powder, and after reduction, this powders has a propensity, because the powders contains a lot of gangues also, they have a propensity for the sticking, because the gangue material from the low melting eutectic, okay, and then they try to stick to each other. So this sticking problem is there in the fluidized bed. That is the major problem, one of the major problem. So this powder try to stick and agglomerate and then make a process problem. So sarcodate process, basically the major invention in the sarcodate process, so they do the reduction by reforming the natural gas to hydrogen. So this reduction is based on hydrogen only, not the CO comes into the picture. You take the natural gas and you reform it such that only you get the hydrogen, and then the reduction take place in the hydrogen atmosphere only. With hydrogen you can reduce it at comparatively lower temperature, and as a result your sticking problem will be less. So this is the speciality of this sarcodate process. So another way, and finally whatever the product is basically briquetized, there is a hot briquetted iron, and then you can charge into the electric arc furnace. Also this is iron carbide is another process where basically you can reduce the iron ore in presence of hydrogen, okay, and and then you can make the iron carbide, CO gas also, CO hydrogen and CO reform natural gas, and then you can produce an iron carbide directly, and this iron carbide basically dissolve into the liquid iron. That is the advantage, okay, you do not have to melt it, basically it dissolves. So iron, so that is the thing. So these are the different DR technologies that are available, okay. Now advantage and limitation of the DR process. So first of all, advantage if you see, no dependence on the coking coal, that is the major advantage. Smaller module size, you have a module size is less, So you can use it, the MSME can use it very nicely at a low cost. That's why the lower capital investment, and if the size is less, then also your space requirement is also less. So you can use it in a very small space economically. Okay. Easier process control and process maneuverability. That is obviously, since the reactor is very small, so maneuverability will be easier and the easier control is possible. Limitations: the final product is solid and has to be melted. There is some energy is involved here. Individual module size is not very large. Specific running cost, that's why very high. And the specific running cost is high because you are not producing large quantity, you are producing less because of size limitations. And as a result, if you see specific running cost become high. For example, $230 per ton compared to $130 per ton of BF hot metal. So in the DR process, the specific running cost is high, especially if you consider the rotary kiln process. For example, it is the 500 tons per day, that is the capacity. So if you want to produce more, you have to use multiple units. So when you are going for a multiple units, obviously your running capacity will be, specific capacity will be high. From the same reactor, if you can produce a large amount of product, your specific energy consumption will be less. But if you want to produce a similar amount of product from a number of units, obviously you will have more energy consumption, because for each unit, maintaining from each unit, you require some external energy. Okay. So low carbon content in the final product, difficulty during the steel making. That is the thing. In the most of the coal-based DR process, the carbon content is quite low. There is around 0.1% carbon is there. So its liquidity is very high. So if you want to melt it, you require more energy. But some gas-based process, usually the carbon content is high, and nowadays you can control the carbon efficiently. So you can produce a DRI with a very high carbon content, more than 2% also, 8%. So then opening carbon become large, so liquid has become less energy, you can melt it. So properties of DRI and the sponge iron. Sponge iron properties, first you must know some of the properties of the sponge iron. The apparent density of final product is around 1.5 to 4 gram per cc. You know the iron density around 7 to 8 gram per cc. Compared to this, apparent density of the sponge iron is so less, 1.5 to 4. Why? Basically the sponge iron, when you see, it contains some gangue obviously. So gangue contains a lot of oxygen. And then also depending on the metallization, okay, so AFU will be there in the system. Suppose you have 80% metallization, so 20% iron will remain in the form of Ustite, okay, that will be connected with the oxygen. So that oxygen also reduces the weight. Besides, the sponge iron contains lot of micropores, okay, lot of pores inside it. So lot of air is there inside. So as a result, your apparent density is less, and depending on your metallization and the quality of raw material, starting raw material, your density of the final product can be 1.5 to 4 gram per cc. And specific surface area is quite high, 0.5 to 4 meter square per gram. You can see very high specific surface area because of presence of the pores inside it. Okay. And this is the sponge iron. As I said, the sponge-like appearance of the DRI under microscope. So if you see the solid sponge and if you take in your hand, it will not look like a sponge, like soft spongy. It is not a soft spongy, it is a very hard material. But if you see the microstructure, you can see a lot of pores. This is the pores you can find. So it's appear like a sponge. That's why it is called the sponge iron. Carbon content varies from 0.1 to 0.15 for coal-based DRI and 2.5 for the gas-based DRI, that I said. This is a 2.5, very high, because you can control it. Nowadays, even higher carbon in the DRI can be imparted, okay, into the advanced DR processes, gas-based DR processes. Another thing, this high porosity and large specific surface area increases the reactivity obviously of the sponge iron, but at the same time, because of this, the sponge iron is also very prone to reoxidation. So, high porosity and large specific surface area of the sponge iron make it very likely to the reoxidation. So, that is not good, because after metallized, if it get reoxidized, your yield will less. So, how it get reoxidized? If it is heated only in 200 degrees centigrade, sponge iron, that is why you cannot preheat it. At 200 degrees centigrade you keep it and then it will be reoxidized. Even at room temperature in presence of moisture, and because the hydrogen generation basically increases the temperature. Therefore, whatever it may be, this is the sponge iron, especially the gas based sponge iron. I will talk about that, because coal based sponge iron is precipitated by a slag layer to some extent. It is a slag layer is there that basically dissolves the pores at the surface. So, it is not that much of reactive, okay, and reoxidation less prone to reoxidation, but the gas based DRI are very much prone to reoxidation. So, some kind of passivation, some passive layer has to be generated on the DRI if we want to use it in the form of cold DRI and transport it to somewhere long time back. So, thing is that you have to passivate the gas based DRI. So, some passivation techniques are in place, I will talk about that thing. But the fact remains that DRI is very prone to reoxidation. So, you have to be cautious. So, DRI cannot be preheated before melting. You have no scope of preheating, because if you want to preheat it, it will reoxidize. Sponge iron should have low gangue. Gangue should not be very high. So, metallization should be high, around the 90% and above. Otherwise, lot of iron will remain in the form of FeO. Okay. That increases the load on the electrical furnace. Besides, the gangue also has to be low. Gangue means other silicon oxide. There is the ore gangue like oxide, like SiO2, P2O5, MnO, all these things, this gangue. That means that is the raw material, starting raw material should be of high grade, the less gangue. Okay. And also the metallization should be high. Then low impurity. The coal based DRI has very high sulfur. Now, when you are reducing the iron in the solid state, one advantage is that it is in the solid state reduction. That is why the impurity cannot penetrate into the DRI. That is why you can see the carbon is in case of the coal based carbon. Gas based carbon, we have higher carbon because of some other technique. Basically, we specially incorporate the carbon into it. I will talk about that thing. Usually, when you produce the DRI, the carbon is very less, whether coal based and gas based, if you just to produce the DRI, and then because in the solid state, the impurity cannot diffuse into the DRI. So, is the impurity become less? Unlike into the hot metal where impurity is very high, because in liquid state impurity can penetrate much faster, the solid state is less. That is why the carbon is very less, coal based you can see 0.1 to 0.15 and also other impurities. But since the coal, but the sulfur can be high. Sulfur high means sulfur basically in the 0.25, 0.06, that is also considered as a very high sulfur. That is why from that point of view, that is the coal based DRI contains lot of sulfur, because non-coking coal, there is those coal contains lot of sulfur, coal contains lot of sulfur. The sulfur get attached with the basically with the, if it cannot penetrate also inside, it get attached with the DRI, and when you are melting, then sulfur easily penetrate. So, coal based DRI has very high sulfur. Okay. DRI, advantage of DRI is that it has low trump element, because scrap has lot of trump element, because you know the scrap is for different alloy steel, the scrap is generated from different alloy steel. So, you have some Some it may contain molybdenum, it may contain nickel, it may contain chromium, it may contain some other elements, because the scrap contains, it is from the alloy steel. So, lot of trump element are there, but DRI do not have the trump element, and sometimes removing this trump element is very difficult. So, DRI contains FeO, which is helpful for the CO generation and bath stirring, because in 90% metallization also some amount of FeO is there, but FeO should not be very high, some amount of FeO is there. So, that is good. Now, some difference of the coal versus gas based DR technology. Gas based DR involves the gas solid reaction. Now, even faster at the low temperature, because gas solid reaction is much faster compared to the, what is that called, gas solid, that is the solid solid reaction. But gas based reaction involve gas solid reaction, even the coal based also involve the gas solid reaction. Okay, that is also involved, but here basically counter current process. The gas is moving from the bottom and the solid is coming. So, they interaction in the gas solid is much more into the gas based process. That is why the faster even at low temperature, that is why the gas based process also can be carried out at very higher kinetics at comparatively lower temperature. Reforming of natural gas produces both carbon monoxide and hydrogen. This hydrogen is a much better reductant compared to the carbon monoxide, both thermodynamically and kinetically. So, that is why the DRI of the gas based process has higher metallization. And in the gas based process, the carbon content of the DRI can vary from 1 to 2.5% through the cracking of hydrocarbons. Some special technology is there. During the cooling process of DRI, the hydrocarbon cracking takes place, that basically deposit the carbon on the DR. So, gas based DR has higher carbon content, so its liquidus will be less. Now, coal based DR, irrespective of the operating condition, the carbon content is always between 0.15 to 0.2. Obviously, high carbon DRI give an advantage in the steel making, lower melting point, higher opening carbon in the bath. And as I said, the gas based DRI are very prone to self ignition and the deoxidation. And the coal based DRI is protected by a slaggy layer outside, as I said. Coal based DRI plants are smaller in size, maximum 500 tons per day, rotary kiln, as I said, maximum capacity is 500 tons per day. So, lower capital investment, but specific investment is high, I have discussed already. And gas based technology are intrinsically cleaner. Coal based DR plants have to be contained with the fine coal and extensive waste disposal. And this is the typical analysis of the gas based and coal based process. You can see the metallic iron is higher in the gas based process, total metallic, that is the total iron is also high, and then metallic iron is high. The carbon is 1 to 2 compared to 0.1 to 0.3 in case of the coal based process. Sulfur you can see 0.02 to 0.05. In the coal based process it is little higher, because it is in direct contact, there is the DRI in direct contact with the coal. And you can see in the gas based process the sulfur is much less, 0.008 to 0.01. So, it is much less compared to the coal based process, because coal based process the DRI is in direct contact with the coal, there is a source of sulfur. And the phosphorus is more or less similar. The ratio between the metallic iron and the total iron, this ratio is called the metallization, and minimum acceptable is 88%. Metallization minimum should be 82%, otherwise large amount of iron will be connected with the oxygen in the form of wustite, and then that increases both the thermal and reduction load of the electric arc furnace, and sometimes it may not be economically viable. Use of sponge iron, you can use it in the electric arc furnace as substitutes for the scrap. You can use it into the basic oxygen furnace as coolant, induction furnace as a feedstock, and you can use the DRI less than 3 millimeter, very fine DRI you can use in the induction furnace. In the blast furnace as metallized iron to reduce the carbon load and the CO2 emission. Sometimes the DRI, if it is not of very high quality, the metallization is not very high, and if you have used a lot of waste material, as a result final metallization is not high, that DRI you can directly put it into the blast furnace, because in the blast furnace, since it is a metallized iron, it will reduce the coke rate and it will reduce the overall CO2 emission. You can use it ladle furnace as a trimming addition, because you are alloying it, so you have to dilute it, so you can use it the sponge iron there. Now, evolution of the share of the EF in the global steel production. Now, why I am directly coming to the electric arc furnace, because when I am producing the DRI, since it is solid, you have to melt it into the electric arc furnace. So, and percentage share of the electric furnace is increasing steadily. Why it is? Because the scrap, you can see any solid charge, now the tendency is there in the world, it is operating with the more of the solid charge. The scrap, DRI are increasing day by day, okay. Because although in India we do not have much of scrap, because our per capita consumption is quite less, but the outside world per capita consumption of steel is very high. As a result, there is the end of life scrap generation is also very high. So, scrap generation is high, and also you have DRI production. So, as a result, solid metallics is increasing. Okay. If you increase the solid metallics, then you need a electric arc furnace, because in the BOF, basic oxygen furnace, it has a limitation of taking the solid charge as a coolant. There is the more than 25% it cannot take, but EF can take in any proportion. It can take hot metal, it can take scrap, it can take DRI in any proportion, because it has this external source of heating. So, if the solid charge goes beyond 50%, it is not a problem. So, since now the solid metallics are slowly increasing, okay, both the scrap as well as the DRI. So, electric arc furnace is also running very high, and now today around 50% of steel is produced by electric arc furnace, DRI scrap route, DRI and hot metal scrap route. Okay. If you see the share of different metallics as a percentage of the total, you can see hot metal is decreasing from 58 to 52% of the charge, okay. And the DRI and the hot briquetted iron, it has increased from 3.4 to 8.1% up to 2010. I have the data showing, but today it is further more. And recirculating scrap, that is means inside the plant that is generated, and this recirculating scrap is decreasing day by day, because of process advancement, the scrap generation within the plant is decreasing. So, 12 to 8 it has become, but collective scrap, that is the end of life scrap, that is increasing, that is after the, so it is increasing 24 to 31. There is more the per capita consumption of the steel, more will be this end of life scrap, that is expected. So, it is 24 to it has increased to 31%. Unlikely, but unfortunately in India, since our per capita consumption is less, and also we are not generating too much of scrap, okay. So, but the scrap is the future production of steel, because by the scrap melting you can minimize the energy, you can minimize the CO2 and everything. So, we have to go for that thing. So, you can see that is the solid metallics, you can see it is increasing, solid metallics is increasing, and the liquid charge, the liquid hot metal charge in the BF, or it is decreasing. In the steel making furnace, the proportion of the hot metal is decreasing 58 to 52, and every cases you can see the scrap and the DRI is increasing. So, and I will just, I have already given an introduction to the SR process, because while I discuss the SR process in detail, I will talk about that thing, but I will not go much into the introduction. The SR process I have already talked. In the SR process, initially the main idea was to melt everything into a reactor, such that we can get rid of all the irregularities that take place into the blast furnace. So, in a single reactor you melt everything, in the liquid state you reduce and produce the hot metal. But later on, basically two-stage process also has come, but these are totally separated process. So, one is the reduction unit, another is the melting and gasifying unit, okay. So that is called the melter gasifier, and the reduction unit is called this two-stage process, and these are totally independently operated, and the off gas from the melter gasifier is used into the direct reduction process, and then that gas come out, and then that gas is also, credit is very high because it is a very CO rich with lot of sensible heat as well as chemical heat. So it has to be used for downstream application as well as for power generation. Otherwise this process will not be very effective, because the smelting reduction process, only problem is that the reactor wise you can use any non-coking coal, you can use, I am just coming to that thing. I'll talk about all these things, smelting reduction, so I am not going in this lecture time is limited now. So thing is, I will just in brief I would like to say that this process is very good, because you can use any low grade material, you can use non-coking coal, you can use inferior grade of iron ore, you can use waste material, you can melt it in a single reactor or in a 2 reactor, reduction reactor and the smelter gasifier, and then you can produce the hot metal. This is a very nice process, but the major problem in this process lies with the fact that since you are burning the coal in presence of oxygen, okay, you are generating, there is an intense heat, and then lot of CO is generated, and the thermal and the chemical efficiency is not as good as the blast furnace. As a result, whatever the off gas is coming, that is rich in the CO, and the sensible heat is also there. So you have to utilize, unless you utilize and the process, you can see this is a very fast process also, and you cannot utilize this total carbon, and the carbon rate or the coal rate is very high in this type of process because of the reactor design and all these things. The carbon rate or the coal rate is much higher compared to the blast furnace, around 2 times, more than 2 times, around 4 times in some reactor. So as a result, the off gas that is coming will be very rich in CO, unless you utilized for the power generation or used for DRI production. This process is not at all economic. So okay, I will discuss about this thing later on in next lecture, and then